So in this section and the next, all right, so we're going to discuss cryptography, this class and the next. All of the materials that I use to present this have been adapted from a professor at another university named James Hamlin. So how do you protect the security of the messages you send? So it's a really important issue in the information age. What are some instances when you send information that you hope will be secure? Yeah. Bank info, yeah. Yes. Credit card info. Yep. Health records. Yeah, Calix. Yep, definitely. Emails, you hope they're private. So now that we keep so much of our information electronically, this has become more and more of an issue, right? We keep things electronically, and many electronics are connected to each other via the internet. So the security of our information is an important thing that we have to look into. So basically, it's largely impossible to prevent messages from being intercepted. There's always going to be hackers who can grab your messages. So since we can't keep people from reading our messages, what we do is we try to disguise them so that the messages only make sense to the intended recipient. And this process is called encryption, the process of disguising a message. So some vocabulary. Cryptography is the study of processes by which information is disguised so that unintended recipients cannot understand it. And encryption is the process of disguising the message, and decryption is the reverse process. A cipher is a reversible rule for disguising a message. So what do you think the word reversible means in that context? Go either way, what do you mean? A reverse? Whatever you do to disguise the message can be undone, right? So you're going to do some stuff to the message to disguise it, to make it unreadable, but we need that process to be reversible because we need to be able to undo what we did so that someone can read it someday, right? Otherwise, it's like you burned it. Okay. So we want ciphers, or here, I'll write this down. The disguising process has to be able to be undone. You have to be able to undo what you did to disguise it. So in general, we want ciphers that are simple enough to use regularly. So they're pretty simple, makes them quick to use, but complex enough so that the messages can't be easily decrypted by somebody who knows the rule, or by someone who does not know the rule. So one of the simplest and first used ciphers is called the Caesar cipher, named after Julius Caesar, who used it to communicate with his generals. So you take the letters of your message and you change them according to this rule. Each letter is replaced by the letter 3 places later in the alphabet. So A gets replaced with D. So you go A, B, C, D. Right? B gets replaced with E, and C gets replaced with F. And then what do you do when you get to the end of the alphabet and you replace W with Z? What do you replace X with? A. You wrap around to the end. So X goes to A, Y becomes B, and Z becomes C. So this is what the cutout things are really useful for that I had you cut out before class, if you remembered to do it. I'm going to snag these. So that they are so that you can line up the alphabet and really quickly translate. So A, line it up with D, and then you've got the whole alphabet lined up, and you have a third copy so that you can put it underneath and see what lines up with X, Y, and Z. That makes sense? So you're going to use these for any kind of substitution cipher that's similar to Caesar. And we'll talk about it more in a little bit. So typically, when you're writing a message to encode, we leave out spaces and punctuation, because knowing the lengths of words in our message could give the enemy a clue about the content of our message, right? If you can see, because one-letter words are either just A or I, right? Those are the only two one-letter words. So we leave out we don't show the length of the words, because then it makes it easy to guess and crack the code. So to help us do problems involving the Caesar cipher and any other shift cipher, you just shift the alphabet a certain number of places. You use the cutouts from page 3. So if you haven't already done so, you can cut them out or just carefully tear them out, whichever. And if you don't, that's okay. You're just going to find yourself writing the alphabet out like 500 times, which is not the end of the world. All right, so when you're ready with your cutouts or the alphabet written out, one on top of the other, I want you to encode the message "attack at daybreak" using the Caesar cipher. Okay, so let's encode "attack at daybreak." Each letter is going to be replaced with the letter 3 after it. You can use your cutouts so that you can make that a really fast process, or you can just think, what's 3 letters after the letter I'm trying to encode? So like A, B, C, D, right? T, U, V, W. And then A becomes D, C, D, E, F, K, L, M, N. A becomes D, D, E, F, G. A becomes D. Did I skipped at T? Where was I? A, T, T, A, C, K, A. W, yep, okay. And then D, E, F, G, A, D, Y, Z, A, B, B, C, D, E, R, S, T, U, E, F, G, H, A, B, C, D, K, L, M, N. So does that make sense how you do that? Everybody got that result? Okay. So to make messages a little bit more readable or less overwhelming to look at, we often split the gobbledygook message into 4-letter blocks, or not necessarily 4 letters, but just blocks of equal length. We'll use 4 for this one. So we have D, W, W, D, space F, N, D, W, G, D, B, E, U, H, D, N. So to decode a message from the Caesar cipher, you go backwards 3 letters in the alphabet. So this message was encoded using the Caesar cipher. I want you to decode it. Okay, so what does it decode to? All work and no play. So once you decode each letter, then you have to figure out where the words are, right? Because we put the spaces in a way to make it difficult to read. So you have to decode letter for letter and then decide, and then try to figure out if it still makes sense. So the Caesar cipher is an example of a substitution cipher, because each letter of the message is replaced by another letter according to a consistent rule. Okay, so the cryptoquote puzzle in the newspaper is an example of a substitution cipher. But substitution ciphers have a big weakness, and that is that the rule for substituting letters is always the same throughout the message. So this makes encoding the messages easy, right? You can just use those little cutout things. But messages can be deciphered if they're long enough, right? So if you write a long enough message, it makes it easier for someone to decode it. And one method that can be used to break a substitution cipher is something called frequency analysis. And that's using the fact that certain letters in the English language are used more often than others. So according to this histogram, this chart, what's the most frequently used letter in the English language? E. Yep. E by far, most frequently used letter. And then A and T are second, right? T a little bit more than A. So if you read through an encoded message, whatever letter is used the most is probably E, A, or T. So you can use a trial and error approach with an educated guess of guessing E, A, or T. Right? And then you can look for common prefixes or suffixes or common short words. And with time and effort, trial and error, you can break the code. So the main problem with the substitution cipher is that the order of the letters does not change. Okay? So more advanced ciphers involve rearranging the letters of the alphabet to try to avoid this problem, to make it harder to break using frequency analysis. So the Bifid cipher is the next one we're going to study. It uses a device called a Polybius square. And they are 5 by 5 grids, which means there are 25 spaces. And how many letters are in the alphabet? 26. So I have to get rid of a letter. So I'm going to get rid of J because it's an uncommon letter. And if there happens to be a J in my message, I'm just going to replace it with an I. And then whoever decodes it will be able to figure out, like, oh, that's supposed to be a J. All right, so the way the Polybius square works is you fill in the alphabet in order. So we could do that now in the above left grid. We're going to go across the rows and remember to skip the letter J. So we just fill in A, B, C, D, E, H, I, skip the letter J, go to K, L, M, N, O, P. So that's one way we could fill in the 25 boxes with the 25 letters. Or we could be a little more crafty about it, and we could create a square based on a keyword of our choosing. So I'm going to fill in this other square using the letters of a keyword going across, and then the rest of the alphabet never duplicating and skipping J. So for this example, I'm going to use the keyword confidential. So I'm going to write out confidential across. I can never repeat a letter because then I'll have used up a box twice for one letter. I'm never going to repeat a letter. And once I'm done with the letters of confidential, then I fill in the rest of the alphabet, anything I haven't put in yet. So I've got C, O, N, F, I, D, E. I'm not going to put an N because I already have an N in my square. So I skip the N in the second N in confidential. So my next letter would be T. Then I'm going to skip the I because I already have an I. Then I put in an A and an L. So I've put in all the letters of confidential, skipping any letters that would repeat. Now I'm going to fill in the rest of the alphabet, any letters that I haven't already put in. So I've already put in A, so I go B. I've already put in C, D, and E, and F, so I skip to G. H. I've already put in I. I always skip J, so I go to K. I've already put in an L. M. I already have N and O, so I go to P, Q, R, S. I already have a T, U, V, W, X, Y, Z. So the most common mistake in here is to put in a letter twice by mistake. And so if you come out and you run out of boxes and your Z has to go over here, you should think, oh, I must have put in a letter twice. And you go back and check. Or if you finish with Z in this box and you have an empty box, you skipped a letter, right? There was a letter that didn't get put in. Okay, so that's how you fill out a Polybius square. Early in your packet, on one of the first pages, there are several blank Polybius squares for you to use in your homework and or on a test. So the process to encode using the Bifid cipher is 1, create a Polybius square using a keyword. So we just learned how to do that. 2, you look up each letter of the message by its row and its column in the Polybius square. So you change it to a set of numbers, its row and its column. So let's do that first. So here's my Polybius square based on the keyword confidential. And I'm going to encode the word retreat. Okay. So for each letter, I look up its row and its column. So I find R in my Polybius square right here. And it's in row 4, column 3. So I put in 4, 3 for row column. Okay. So what 2 letters would I use for the letter E? 2, 2. Row 2, column 2. How about the letter T? 2, 3. Good. 4, 3. E we said was 2, 2. A is 2, 4. T is 2, 3. And I tacked on an X to the end of this message because, as you'll see when we decode, we have to have an even number of letters in a message in order to use a Bifid cipher. So if you have an odd number of letters, you just tack on something at the end to make it even, like an X or a Z, something uncommon. So X is 5, 3. All right, so that's step 2, right? We've looked up each letter of our message. Step C is to group the number in pairs, reading from left to right this time. So now I'm grouping in pairs from left to right. 4, 2, 2, 4, 2, 2, 2, 5, 3, 2, 3, 3, 2, 4, 3, 3. So that's step 3, group the numbers in pairs from left to right. Last step, look up these new pairs of numbers in the Polybius square. So remember, the first number in the pair is the row, and the second number is the column. So they always go row, column. So I'm going to look up 4, 2, that's row 4, column 2. That is the letter Q. And then I'm going to look up 2, 4, row 2, column 4. That's the letter A. 2, 2 is T. 2, 5. 2, 2 is E. Oh, sorry. Thank you. Okay. 2, 5 is L. 3, 2 is G. 3, 3 is H. 2, 4 is A. And 3, 3 is H. So there's our encoded message. The word retreat encoded. Retreat X, yeah. That's a what? Painfully long process? Well, it has an advantage though. It is longer, but is it a substitution cipher? Does each letter always become the same letter? No. So for example, the letter E, right, is the second letter of the message. It becomes A here. And then later in the message, when it's the 1, 2, 3, 4, 5th letter, it becomes a G, right? So each letter doesn't always get encoded as the same other letter. So it is a little bit longer in process, but it has the advantage of not being a substitution cipher, so it's much harder to break. So this is no. E becomes A, and later E becomes G. So it's not just a substitution cipher. To decode a message, you reverse this process. So you look up each letter in the Polybius square, write down the row and then the column, but write them from left to right because we're going backwards, right? So that you write them from left to right. Then you split the message in half, put the second half below the first half, and read the numbers vertically to decode. Okay. So I'm going to have you start by filling out the Polybius square, and then we'll finish decoding it together. So we're going to use the keyword Schwarzenegger. Fill out the Polybius square with that keyword. All right, let's fill out our Polybius square together. We start by trying to write out the word Schwarzenegger, left to right, skipping, never repeating a letter. So I have SCHWARZE. That's an R. It's going to be hard to see later. There we go. EN. Skip E because I already have one. G. I only write it once. Skip E and R. So, okay, so that's all of Schwarzenegger without any repeated letters. And then I fill in the rest of the alphabet. I already have an A, so I go to B. I already have C, so I go to D. I already have E, go to F. I already have G and H, so I go to I. We always skip J, so we go to K. L, M, we already have N, so we go to O. P, Q. We already have R and S, so we go to T. U, V, W, X. Which is perfect. We already have T, U, V. We already have X, Y. Yeah. Already have a W, X, Y. Okay. And it makes sense because there is already a Z in Schwarzenegger, so that's why we finished on Y. All right, so now we're going to look up each letter of our message. So I'm going to write it out bigger. That's sort of a common, just good practice. First, write out your message bigger so you have room to B, T, B, K, K, S, T, V, L, A, A, A. Okay. Then we look up each letter, and we're going to write down its row and its column left to right. So when we were encoding, we wrote down the row and column vertically. When you decode, the first way you write it is horizontally. So I look up the S, and that's 1, 1. So under my S, I put 1, 1. Under my A, I put 1, 5. Row 1, column 5. Under W, I want 1, 4. And A, 1, 5. B, 3, 1. T is 5, 1. B is 3, 1 again. K is 3, 5. 3, 5. S is 1, 1. T, 5, 1. V is 5, 3. L is 4, 1. And A is 1, 5. So I have 1, 5, 1, 5, 1, 5. Then I want to find the very middle of my message, right? So I want to find the very middle. I have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32 numbers written across. So I want to cut it in half. So I'm going to cut it at 16. 2, 4, 6, 8, 10, 12, 14, 16. Cut it in half. Then I'm going to take each of these numbers and write them below my first set. So I'm going to take my 3, 5 and put it underneath my 1, 1. And then my 1, 1 and my 5, 1 and my 5, 3, 4, 1, 1, 5, 1, 5, 1, 5. Then I read all of my pairs vertically. Then I look up all my vertical pairs. 1, 3, 1, 5, 1, 1, 5, 1. So I look up row column. 1, 3 is H. 1, 5 is A. 1, 1 is S. 5, 1 is T. 1, 5 is A. 4, 1 is L. 1, 5 is A. 5, 3 is V. 3, 4 is I. 1, 1 is S. 5, 1 is T. 3, 1 is B. 1, 5 A. 3, 1 is B. 5, 5 is Y. So what does it say? Hasta la vista, baby. Yeah. Oh, did I miss an A? Vista. I missed an A there. Hasta la vista, baby. So, to summarize, when you encode, you look up each letter in the Polybius square, oops, and write down row column vertically, then regroup them horizontally, right? And then when you're decoding, you look up each letter in the Polybius square, write them horizontally, then reorganize them vertically. So encoding, vertical to horizontal, decoding, horizontal to vertical. All right, so here I have some little group work for you. Feel free to use the Polybius squares on page 3 in the group activity and or on the homework. And this is a group activity for the remainder of class. And I want to point out your homework. There's no My Math Lab assignment for this section. So you're going to do the textbook assignment, which isn't really a textbook assignment. It's all written in the packet. So this is your homework. 1 through 7. 1 through 7. Yep, due next week.